Stop now. Yeah, yeah.
Oh,
Thank you.
yeah.
Good.
Okay, thanks. Unlike I cannot write when it's up there. Okay, so to join, what I'm going to speak about joint growth is Marc Burger. And some of the motivation, thanks to kind talks of Emmanuel, the motivation is about lattices and product of trees. And so we look at suppose you have gamma on T1, on T2. So T1 and T2 are some regular trees. And gamma is co-compact lattice. And so some of you want to understand this type of group and what group can you write. That we want, in order to have nice structure theory, you need to know something about the projections. So one is to understand, let's denote it by HI, the projection of gamma on the ice tree and take its closure. So really gamma sits in H1 plus H2. And we would like to understand what kind of group this can be. So one obvious necessary condition is clarity. That since we are assuming that this gamma is co-compact, then it's easy to see that HI is topologically finitely generated. Oh, well, not HI, I want to look at HI X. So HI X is the stabilizer of some vertex, of a vertex X in HI. Okay, the reason is very simple. If you look at the tree, at one of the trees, so say you look at T1, you look at the vertex X, and you look at the stabilizers. Look at the stabilizer of X in H1. Let's say O3. This is an open compact subgroup. Let me call this maybe K. So if you look at K cos the second automorphism group T2, this is an open subgroup of this big group. So this intersection with gamma is a lattice in K cos T2 is a lattice, And now since K is compact, I can project it. So really this group is actually a lattice, a co-compact lattice in one tree, and it's finitely generated, and this gives you the finite generation, topological finite generation of the projection. So one immediate corollary of this is, for example, that such lattice gamma cannot have dense projections. So the corollary. So gamma of T1 of T2, a co-compact lattice. The projection of gamma, say, on the first tree is never the full automorphism of the tree. And I think I'm going to use just this one. And the reason is the following. If you look at one tree, and you look at stabilizers of a vertex, and you look at the full automorphism of the tree, and you look how it acts stabilizing the vertex, then what you see, you preserve the sphere around the vertex, and each one has a permutation group. So you can look at the sign of the permutation, right? So you have a map from this, we have K, now it's just one tree. So K is the stabilizer of some vertex x0, 0, and not 3. And so you have a map from K, right, to, if you want to 0 to 0 to the n. Just look at for each integer, look at the sphere of radius n around this vertex x. 0, look at the notation, look at the sign. And of course, this group is not topologically finely generated. Whenever you have some non-trivial group, so the infinite product of it is not topologically finely generated. Okay. So this is. Okay. Now, a natural class of group that you can study acting on the tree is the following. So suppose we have the tree and we we have some irregular tree. And color at each vertex, at each edge, color the edges by D color. Okay. So suppose you take a tree and you color each, and now you can describe it and you fix. So that's following, let's fix permutation group A. So fix some F, some permutation group. Okay, so fix some permutation group on D elements and color the edges of the D regular tree. One up to D, so each vertex you see all colors. And now you can look at, if you take any map tree to itself, any element of the physical group, you can look what it does locally. So each vertex, it goes to some vertex, but then there's some local permutation. So let's define U of F is the set of L elements of T, and that the local actions of G, each vertex belongs to F. So we call this the universal group of F. And the question is what we're trying to understand is what kind of such groups can occur as projection. So we constructed places where you can find alternating groups. Diego Ortagi, part of the list that Pierre Mel mentioned yesterday, he also constructed all kinds of examples. He found all kinds of multi-groups, all kinds of groups occurred. Now, so the question we want to understand is when this group topologically finally generated. So it's necessary, so this is the question we are going to forget about, I'm going to say so far. And the question, when is US topologically finally generated? Okay. So we saw before an obvious condition, right? That if you had the full symmetric group wasn't okay because it has this abelian quotient. So one condition, and now it's easy to see that it's more convenient not to think about F, but suppose you look at the tree and you stabilize the ball of radius 1, okay? And then you begin to look how you act the next level, then you see that what you act there is the stabilizer of this edge. So from now on, let's assume F is transitive. That's one assumption. And because of this assumption, actually we are going to be really interested in the following group, L, which is F1, the stabilizer of 1 in F. And it's easy to see that to understand when this group is topologically finite, to understand this group, you want the stabilized group all of phi. This one is essentially the risk product. So we're actually what we're trying to understand is the risk product if L with itself infinitely many times. So maybe I could call this Ln is risk product and time, and we are going to be interested in a group, let's call it L hat, which is the inverse limit. Oh, I'll call it L infinity of L. Okay, so this group, you just look at
Can you recall how they map one to the other?
I'll just recall what this group is, not as a risk product, but the same director. Okay, so we are looking now at the. So we have maybe D will be 2 up to this, set of size D minus 1, and I look at D to the n, we call this Sn, so that's, if you want, is the n sphere, but really only of 1 over D of the tree, it's the only thing we care. So, right, so L, which is just S1, right, acts on S1, which is just D. Okay, and in general, what we have is Ln will act on Sn. So it acts on this points and distance. So we have this rooted tree, if you want. We have this. So D was 4 here, etc. So we look at the Sn, this nth level. So Ln will act on this level. And then you look at Sn L to the Sn, you look at map from Sn to L, and you take the same indirect product of this group. Okay, so that will be Ln plus 1. Okay, so that's what we call that. That's what's called the risk product. And you try to understand when is the limit of this group topologically finitely generated. So here are two obvious necessary conditions. So necessary conditions is that you can't, if you had the abelian quotient of L, then of course you can do the same thing as before. So the first one is L is perfect. There's no abelian quotient. L equals its complex. So that's one obvious condition. And another one, which is easy to see, is that L has no fixed points. Right? What does it mean that L will have a fixed point? Suppose L fixes this edge. But then here it fixes again an edge and an edge. So there'll be a path which is fixed. And then so you look at this fixed path. And just out of this path, the tree grows. So you just look at the first level and you see how L acts here. So you get a map. Since you fix this path, you get a map from L infinity to L to the n. And again, this cannot be topologically finite. Any infinitely many elements will have repetitions. All the coordinates. This won't be. It won't generate the denser. Okay, so these are necessary, and what I'm going to describe is good, these are sufficient. The theorem said Marc Burger is that L infinity is topologically finitely generated if and only if these two things hold. And actually I'm going to prove something which, well, at least a priori is stronger. We're going to show not finitely generated, what's called positively finitely generated. So definition. So let K be a compact group. K is positively finitely generated if for some integer k, the set of elements g1 up to gk and k, so that they generate g1 to gk, they generate a dense subgroup. So this set has positive measure. Okay, so this is Shahar measure, so this is Shahar measure, so mu is Shahar measure. K to the okay. So you choose k elements, for some case you choose k elements at random, you have positive probability of generating the group. Now, a priori this is this is not equivalent to being topologically finite generator. There are examples, for example, if you look at the free profile group of two generators, okay, so of course, so PFG implies topologically finite generation, but it's really stronger. If you look at the free group on two generators and take it for finite completion, then this is of course two generators, but not European. The way to see this is an argument of Cantor Vygotsky. The idea is that you show a sequence of finite two generated group, so that for each one of them, the probability of being generated by k element goes to 0 for any k. And it's an exercise, I don't know, you look at an with n factorial over 8. This is two generated, but for any k, the probability goes to 0. N goes to 8. Okay. So we just set them up now. Actually, we just put the manuscript on the archive last Friday or something like this, and immediately got an email from Lassie Piver saying that he and Heike and Shapiro showed that for this product, topologically finite generated of this type at least, topologically finite generated is equivalent to being positively finite generated. As he said, showing that we don't know how to show it finite generated without showing the positive finite generation. So he said it might be the more difficult part. Okay. So I want to say something about what this slide is proof, the idea is proof. So we're going to use an idea of Menakshi potentiality. Okay. 94. And what she observed the following. So suppose you have a, okay, let me adapt what she said in this context. So we have Ln, right, which, if you want Ln plus 1, was Ln semi-direct product with L plus N. The group, and we were trying to estimate, we want to estimate the probability of, so pk of Ln is the probability that k elements generate L. And so here is the position. Okay. Suppose you have two groups. You have a group Y, subject the group X, groups, find groups, and then the probability of generating Y is at least 1 minus sigma, write here the formula and explain the notation afterward, 1 over the index n in Y, k minus 1, time the probability of generating X, where the sum is of all M quadratic classes of M inside G by X. So what is GYX? So GYX, maximal subgroups of Y mapping onto X. Okay. So it's an easy observation, right? You know that if you choose K element, you want to generate Y, so you can, right? So PK Y is the probability that you generate Y given that you generate X, and probability to generate X. And now if you don't generate, if you take a collection of elements, if they don't generate Y, then they generate some subgroup, so they like some maximal subgroup. So you can go over all maximum subgroup and somehow estimate. Okay, so I mean, it's not difficult anyway. Yeah, now, we are now looking at these are variables. So we're going to apply this for Ln plus 1 and Ln. That's the case what we are going to look at. Okay. And to get this, it's just an easy estimate just from this, and you just the observation that if you don't generate any line in some subgroup, hence in a maximal subgroup, which has to surject, and then so actually you have to look at 1 over the. So if you look at the probability that you're inside M, some maximal subgroup divided by Y to the K, like that's the probability that your K element lies inside the group, but then you have to look over what the conjugate, you have to you sum it over the conjugacy classes, so that's give you type Y normalizing Y of M, and this gives you this power. This is 1 over. From this you get this estimate. Okay, so once you have this, the claim is the following: that if we now define zeta y given x of S, the sigma of all these conjugacy classes of maximal subgroups, 1 over the index of M y to the S minus 1, oh, back to S, just to S. And then the corollary, if assume for some K greater than 2, look at the sigma of the zeta, but now for Ln plus 1, given Ln of K minus 1, let's maybe call it K1. It's finite. Okay. Then implies that N infinity is P of G, with K you can take something which is bigger than equal to maximum between this K1 and K2, where K2 is chosen so that Ln1 is generated by K2 elements, and this N1 is sort of this sum, and sum N goes from N1 to infinity zeta ln plus 1 ln k1 minus 1 is smaller than 1. So this is just this. If this converges, then this like you have to look at the product of 1 minus this sum. So I'll be 1 minus this zeta. Okay, so if the sum converges, this product is positive. So, okay, so we need somehow to estimate this sum. And so the main thing is to understand this maximal subgroup. Like you take here a sum of all maximal subgroup of this product. And so let's set up. The setup is the following. So we have some set, we have some finite group X. X is a finite group. In our case, it's actually going to be an N. And it acts on some state omega. And omega decomposes into X orbits. Omega is going to be omega 1, omega 2, omega 3. So all of this is finite. So there is some finite and okay. For each I between 1 and t, we are going to have some b1, b2, bt, some perfect groups. And we are going to look at the group y, which is f semi-direct product with b1 to the omega 1 plus b2 omega 2 bt to the omega 1. So actually it looks slightly more general than our ln semi-direct than our risk product, but you'll see why we need it. Clear. So we need to find some definition. So if you look at the group, the subgroup of M of y, subgroup M in y, or maybe no, for N, let me say subgroup N, subgroup. A normal subgroup. And in y is called standard. What are the obvious normal subgroup you can find here? You just like, this is the normal subgroup, and you can take normal subgroup to be I. If you take the form, n equal some n1 to the omega 1 n2 to the omega d for some ni normal subgroup. And we'll say that the maximal subgroup is clean, or subgroup n is clean, so m in y is clean. It does not contain any non-trivial standard subgroup. It does not contain any non-trivial standard subgroup. Okay, so before I state the main technical thing, the idea is going to be the following. We are trying to estimate some overall maximal subgroup. So what we're going to do is to take any maximal subgroup. Inside this, we can look at the maximal standard normal subgroup and divide by it. When you divide by it, you get a clean subgroup. But now, before we started with something which was the form Ln semi-direct product, this L to the Sn. When you divide by some standard normal subgroup of this, you get something of this form. And then you have to understand clean maximal subgroups. Some of to do estimate for them. And okay, I don't know anything better than to tell you the main technical thing, which is the reason it took us many years to write it down.
Could you lift this board and use this?
I need another, I don't know, 10, 20 centimeters to do this. Can try. Yeah, okay. I'll try. I can write here, I don't know if you see it. Okay. Okay, so the main, so here's the proposition. I apologize in advance. So we're in this setup that is half raised above, and so we have m inside y. So y is this x semi-direct product is pi of bi to the omega I goes from 1 to t. Is a clean maximal subgroup. Okay, then one of the following words. Okay, T is this one. Okay. Otherwise, might be triggered this. Okay. So first possibility is T equal to. And then you have just B1 and B2. These are non-abelian simple groups. And here A first thing, if you look at M, intersection is B1 to the omega 1 plus B2 to the omega 2. This is a graph. It's a graph of an isomorphism in B1 to the omega 1 to B2 to the omega 2. So in particular, we already know that B1 and B2 actually is isomorphic to some degree. This tells you B1 is isomorphic to B, B2 and omega 1 is of the same size as omega 2. So that's one thing that you know. And yeah, I think it's better if I write here rather than put it down. Down and so I have some problem with my knee, so I cannot really leave it down. And the second part of this, I'm going to say that M is actually the normalizer of this graph. Y of this intersection. And then you know that there is a, so this implies that at most the size of omega 1 times the size of the outer automorphism group of B1, which is the same as B2, conjugate classes. Such subgroups. once you fix the B1. And then B1 and B2. And the indices, and the index of y and n is at least B1 to omega 1. Okay, so that's one case. Some of the simplest of all the four cases. Second possibility is the t equal 1. Actually, there are going to be four possibilities. I'm not sure I'm going to write all of them. But either we have just two orbits or we have just one orbit. And if t equal 1, okay, then there is 1 to the t equal 1 and n intersection b. Now there's only b to the omega is not trivial. And then if you look at the projection in one of the coordinates of this intersection, this is all of b. So this is for every omega. There is a normal subgroup u inside b, which is actually u is of the form t to the r, where t is some nanobillion, t nanobillion simple group. Okay. Okay, maybe yeah. And then there are just you get something about the. So we know the structure of this is a product. It's essentially a product of subdiagonals. Maybe I will not write all the details, right? So you have like this t to the r, and then you have t to the r to the omega, and you have a subgroup which is really just product of subdiagonal mean that some don't repeat themselves, but then a diagonal is just a graph of some automorphism. Okay, this again you'll have that n is determined by this intersection. And there is some bound on the number of conjugacy classes. And okay, and there is again an estimate, which is the size of this group, T, this simple nanobillion group, to the R to the size of omega over 2. Which is, if you want, it's just U, it's not subgroup U to long problem. Okay, then maybe I'll just write that there are another possibility that again T equal 1, but now that this intersection B omega is not trivial, but the projection of the intersection is a proper subgroup. And again, you get some bounds of this type, and the fourth case is that equal 1 and this intersection is true. Okay, so what one needs to know from this proposition mostly, and I illustrate maybe just in the first thing, that you get a very, very fine structure of what are these clean maximal subgroups, and what is the index. Now, maybe something to justify why this has to be somewhat technical. I said we learned later there was this result of Piper and Haken. where they show that finite generation in this case is actually equivalent to this positive finite generation. Their argument uses the classification to define a simple group. Okay, so somewhere you need to put something, so we at least avoid it. Okay. Maybe I'll keep this part, like what you do now. Okay, so now what we'll do, we look at we're trying to estimate, so now we need to estimate this zeta of Ln plus 1 given Ln. Okay. So what one has to do is the following. So we take some M, a maximal subgroup of L plus 1, so that if you look at the, so there is a map, right, pi from Ln plus 1 into Ln, so we want that pi of M is Ln. And then we take MS, and it's going to be a maximal standard normal subgroup. And this makes sense, right? Because you take two standard normal subgroups, the product is again a normal standard subgroup. So there's a well-defined what we mean by this maximal thing, and then you just look at y, which is going to be Ln plus 1 modulo this ms, okay, and our x is going to be x modulo ms, ms. Okay, so we're back in the situation that we okay, I have to look and use m modulo ms. Now it's a clean maximal normal subgroup. And so we're in the situation of proposition, and well, one thing to note is that you really have t exists 1, because if this maximal standard normal subgroup contained, if ms was this L to the Sn, then you'll have that you divide it Ln plus 1 modulo Ln will be just, modulo ns will be just Ln, but you surject and you'll be everything. Okay, this would imply that m will be equal to Ln plus 1, that m is proper. M is proper. Okay, so we are in the situation at the end, and now we just need to look at the contribution. So we have to look at each of these 4 cases, and let me just say, for example, what happened if you now. So we have to understand this orbit, right? So we have this set. So now we have omega 1 and omega 2, these 2 orbits. Actually, these are really orbits of Ln. So if we had D up to, this is our set of size D minus 1 on which L acts. And so this decomposes into blocks, right? Into some D1, D2, dr. And the important thing that each di is at least 2. Okay. So now what happened at this that if you look at this the orbit of this omega 1, each of these omega I, its size is going to be at least 2 to the n. Right? Because how do you get an orbit in the nth level, right? You have the orbit in the nth level, Sn is d to the n. Right? So to take an orbit, so this is the union of all di1 plus di2, din, and ij is between 1 and r. These are the possible orbits, and the point is they're all large. That's really where we use this thing is where we use it. You have no fixed point in this argument. And now, okay, I have to just 1 minute. Yeah, you see the contribution from 1. Okay, we have to estimate the number of. I mean, each summand give you 1 over this index to the k minus to the k, right? So each summand gives you 1 over 1 m to the k, which and this is smaller than 1 over b to the omega. Now, okay, this b is some simple thing, so it has at least, this is the size at least 2. Okay, so this is at least 1 over 2, and the size of this omega is at least 2 to the n. Okay, so each one of them give an extremely small thing. And it's so small when you calculate how many, you have to, actually the number of summand in this case is not so large, you have to look at the number, so C1 will be just the number of simple quotients. Of L, and then you have some bound on the, so there is some upper bound on, outer automorphism groups of such quotient, Anyway, all of these are finite things, and what you get is you get eventually just some r to the n over 2. This is the choices of two orbits. Okay. C1 squared or C2. Okay. 1 over, well, you have the size of omega, let's say size of d to the n, divided by 2 to the n, or this by k, but here k is irrelevant. So everything here you see is just some exponential in n, and here you have something which is doubly exponential. So this here. And now we have to, I won't do it even also because you need to write the whole other 3 cases, but in each one of them you have to do this rather carefully. In all first 3 it's easy, you have kind of a lot of spare. The last one is you have to work, but it's still, I mean, the estimate still works and you get it converges. Okay, so I should stop.
Can explain how you pass from finite number of rest products, finite size rest product to infinite size.
Just the induced limit.
Yes. And now, when this lower bound on probability.
You mean how I pass, not the finished group, how I get to the probability?
Yes.
So I have my group is a. So we have the following situation, right? We have Ln plus 1 less than Ln. Right. So I can think, maybe I can think concretely of my group, as. So L infinity, you can think of it as a. As a omega in product of this Ln, so that omega is some sequence Gn, then I can call this plus 1, then I want the Pn of Gn. So these are the concrete way of thinking of it. And now I want to calculate the probability now, but I have to. So if you want, the probability is just it's coming from the product, right? So I can estimate each level and get more and more refined thing. Okay, so if you how to say it in a good way.
No, I believe you.
Okay, once you look at this, then you think.
I believe you. The measure of these frequencies.
Yeah. I know. If you want to do the following, here, let me say it this way.
Okay,
Let me say it without this. Take k elements. At Ln, you look at k elements. You take limit set of this. You have each stage you have a set of of measure at least 1/100,
Yes.
right? And now you look at the limits. Still, the measure cannot increase. You cannot compress it somehow.
That your proposition, so it tells us it's a description of maximal subgroups in Brest products. So
No, it's really
it's not the generality.
No, it's not the. It's really semi-direct. It's a maximal subgroup. What you say? We look at. This is a specific type of risk. We look at the X semi-direct product of some. Just look at things at the upper level, and there you assume things which are clean, and then we know exactly what the structure is. So if you take a maximal subgroup, it means that if you take a maximal subgroup with such risk product, then actually almost all there may be several orbits. All of them are full except at most two, except one or two. That's really. And so this is really, the difficult part comes from the fact that our group L does not act transitively on D. There were previous results by people when they assumed that L was acting transitively on the set. It simplifies a lot of the argument somehow. Some of the difficulties because you have to deal with the fact that you're not transitive. Part of the difficulty is for us.
That you have no fixed point at infinity, but this enter the argument.
That's what I said here. That the fact that the size of the orbit, the size of omega 1 was at least 2 to the n. When you look at the nth level, right, it's at least 2 to the n, because how do you get orbits in the nth level? You take orbit in each level and multiply them. And each one of them is 2, so that's why you have the 2 to the n, and this 2 to the n is this 2 to the n. Otherwise, that's how you get this super exponential process exactly from this. That's what the reason I wanted to show this.
No more questions. Let's thank you again.